Hi, myself is Dr. Prabhakar Rapaka, working as an associate professor in the Department of Electronics and Communication Engineering, Reddy Institute of Technology and Management. So today I am going to explain about the course Analog CMOS IC Design. So this Analog CMOS IC Design is one of the important subjects in the VLSI areas, especially for IC designing, IC industries. So here, this subject, it requires the prerequisites are knowledge on the circuit design, microelectronics, analog electronics, and familiarize with the EDA tools like KiCad, CZ, EDA, PSpice, etc. This course objectives are familiarize with the MOS devices and its modeling. Next one is learn and design analog CMOS circuits, analyze CMOS based amplifiers, frequency response and its noise. Next one is learn and design operational amplifiers with CMOS technology. Next one is stability and frequency compensation of analog CMOS circuits. Course outcomes are, at the end of this course, students will be able to analyze different CMOS device models and circuits, design differential amplifiers and current mirror circuits, analyze trade-offs in frequency response and noise models, design and analyze two-stage operational amplifiers with the measurement techniques, analyze two-stage op-amps, frequency compensation and stability. The course contains, there are 5 units. So unit 1, basic MOS device physics. Unit 2, differential amplifiers and current mirrors. Unit 3, frequency response and noise. Unit 4, CMOS operational amplifiers. Unit 5, stability and frequency compensation. So in unit 1, we can able to study the introduction of MOS devices and MOS IV characteristics, second order effects, MOS device models, single stage amplifiers, common stage, source followers, common gate stage, cascade stage. These topics are covered in the unit 1. Coming to the unit 2, differential amplifiers and current mirror circuits. So here, single-ended and differential operations, basic differential pair, common mode response, differential pair with the MOS loads, Gilbert cells, basic current mirror circuits, cascade current mirror circuits, active current mirrors and biasing techniques. These topics covered in the unit 2. Coming to the unit 3, here frequency response and noise, common source stage, source follower, or differential pair, gate bandwidth, trade-offs, statistical characteristics of noise, types of noise, representation of noise in circuits, noise in the single stage amplifiers, noise power trade-off, noise bandwidth. These topics covered in the unit 3. Coming to the unit 4, CMOS operational amplifiers. So general considerations, one stage op amps, two-stage op-amps, gain boosting, compensation, hot swing calculations, common mode feedback, slew rate, high slew rate op-amps. Coming to the unit 5, stability and frequency compensation. Multiple systems, phase margin, or basic frequency compensation, or compensation of two-stage op-amps, slewing the two-stage op-amps, Nyquist stability, Nyquist criteria, non-linearity and mismatch. So for this course, textbooks are, first one is design of analog CMOS integrated circuits by B. Rajavi, Tata McGrail, second edition 2017. Second textbook is CMOS analog circuit design by Phillips, Oxford University, second edition 2010. Unit 1, Basic MOS Device Physics. Unit 1 contains the introduction to MOS devices, general considerations, MOS IV characteristics, second order effects, MOS device models, single stage amplifiers, common source stage, source follower, common gate stage, cascade stage. Before going to the subject, we should know the basic basics on the MOS. What MOS means here, metal oxide semiconductors. So generally here transistors are two types widely used in our electronic circuits. So they are one is bipolar junction transistors and field effect transistors. Under this field effect transistors, there are based on the technology we are consider MOS technology. So here FETs are of two types. Here field effect transistors. Here these FETs are generally considered MOSFETs. So metal oxide semiconductor field effect transistors. So the MOS refers to the basic structure used in the MOSFETs. They are metal oxide semiconductor field effect transistors, which are building blocks of modern digital ICs. It consists of three layers, so stacked on the semiconductor. One is a metal gate, and second one is oxide layer. Usually silicon dioxide layers are used. Next, third one is semiconductor substrate, either P-type or N-type substrates. MOS structure is first studied as a capacitor. So here metal is considered as a one plate, a semiconductor considered as a second plate, oxide layer considered as a dielectric. So depend upon the gate voltage, the surface of the semiconductor undergoes accumulation, depletion and inversion. So here accumulation means more majority charge carriers. So depletion means removal of major charge carriers. Inversion means minority carriers from a conductive channel. Here you can see the MOS transistors. So here source, gate, drain. There are three terminals. Substrate. Here gate terminal. So here the structure of the MOS transistor consists of substrate, source, drain, gate and channels. So first one is substrate. So substrate is typically made up of silicon, that is semiconductor material. So it can be either a P-type or N-type, or depending upon the doping level. Next one is source and drain. Here heavily doped regions are created in substrate. So source, where carriers, electrons or holes enter into the transistor. Drain, where carriers exit the transistor. Next one is gate. It is a conductive material. like generally polysilicon or metal, which is placed in the substrate, but insulated from it is by a thin layer of oxide, either silicon dioxide, which controls the flow of current between source and the drain by modulating the channel. Next one is channel. So channel is the region between the source and drain. So here this is the channel between the source and drain. Conductivity is controlled by the voltage applied to the gate. Generally, these MOS transistors are of two types based on the channels NMOS and PMOS. So first consider the NMOS channel. So here NMOS transistors are characterized by the use of N-type. They are negatively doped semiconductor materials. So for the source and drain regions, while the substrate is made up of P-type doped semiconductor material. Here this N plus indicates the N-type materials. Here P indicates the P substrate. When the positive voltage is applied at the gate terminal, then NMOS transistor, the electric field is induced across the oxide layer, which attracts the free electrons in P-type substrate, forming an N-type conductive channel between the source and drain regions. That means whenever here the positive voltage is applied to the gate terminal, so here the free electrons are here in the field of free electrons are attracted by this silicon dioxide layer, and which forms the here N channel between the two N-type materials. So that forms the N channel while applied positive supply to the gate. This is the NMOS symbol. So this NMOS symbol here consists of here when gate voltage is 0, this NMOS act as a open switch. When gate is equal to 1, then it is act as a short circuit. The advantages of NMOS: high electron mobility, faster than PMOS, small size for same driven strength, good for pull down networks in CMOS logic. So your high electron mobility means in N-type material your electrons are heavily doped, hence more electron mobility available in the N-type MOS. Disadvantages: consumes the static power if it is used alone. When conducting requires resistive load. Next one is less power efficient than the CMOS. Applications of NMOS are logic gates in early digital ICs, pass transistors, switching circuits, use of the pull down in the CMOS logic. Amplifiers in the analog ICs. Next one is PMOS. So in PMOS, here majority charge carriers are holes the doping with the P-type material to the MOS transistors. Then here it is more number of holes are added to the MOS. Then it is called as a P-type MOS or PMOS field effect transistors. PMOS transistors here have the P-type semiconductor material for the source and drain regions, while substrate is composed of N-type semiconductor materials. Here these two are the P-type materials, and this one is substrate is N-type material. When negative supply applied to the gate, here the electric field across the insulating oxide layer attracts the hole from the N-type substrate. Here create a P-type conductive channel between the source and drain regions. That means here whenever negative supply applied to the gate voltage, here by the silicon dioxide layer, here more holes are attracted and here p-type channel is created. The symbol for p-type, you can observe here, so a small bubble that indicates the negative input for the gate. So you can observe this is the difference between the n-type and p-type symbols. If G equal to 0, gate to supply equal to 0, this PMOS acts as a short circuit switch and gate voltage is 1, then it acts as a open switch. The advantages of PMOS. So here also this PMOS is used as a pull-up operation, so which connects to the VDD directly and complements to the NMOS in CMOS design, and less prone to leakage in the same configurations. Disadvantages are lower speed due to the lower hole mobility. It requires a larger area to match the NMOS current drive. Used less often by itself. Applications of PMOS are pull-up networks in CMOS logic gates, high-side switches in power electronics. Next one is CMOS. So this is our actual subject concept. CMOS means it is a complementary metal oxide semiconductors. So it consists the PMOS and NMOS, which is nothing but a CMOS. So both the NMOS operations and PMOS operations, NMOS advantages and PMOS advantages are available in the CMOS. So the name CMOS stands for the complementary metal oxide semiconductor. Your complementary refers to the use of both N-type and P-type transistors in the circuit, which works in the complementary manner. Metal oxide semiconductors. This describes the structure of the transistors used in the CMOS technology. Pull-down network. So a collection of N-type MOSFETs that connect the output to the lower voltage power supply rails like VSS or ground. Next, pull-up network. A collection of P-type MOSFET that connect the output to higher voltage rails, VDD. See in the figure here, this is nothing but a NMOS and this one is PMOS. Advantages of CMOS: very low static power consumption, on drawn power during the switches, high noise margin, good reliability, high packing density, ideal for VLSI, scalable with technology modes, no need for resistors in the logic design. Disadvantages of CMOS: more complex fabrication, it requires the N-well or P-well process. Slightly slower than the pure NMOS logic due to the added PMOS transistors. Latch-up risk if not designed properly. Latch-up is an undesired short circuit condition in the CMOS ICs where the parasitic structure causes high current to flow continuously, potentially damaged or destroyed the chip. Applications of CMOS. These are used in the microprocessors, Intel, AMD companies, memory chips, RAM, ROM, flash memories, ASIC and SoC designing, mobile devices and image sensors, FPGAs and VLSI circuits. BiCMOS. So BiCMOS is a combination of CMOS and bipolar junction transistors, which are very useful for the analog as well as the digital designing. So that means a hybrid technology that combines CMOS transistors for low power digital logic and bipolar junction transistors for high speed and high gain analog performance. Fabrication includes the CMOS and BJT process on the same chip. CMOS handles the logic control. BJT amplifies analog and output driven strength. Advantages of BiCMOS: high switching speed due to the BJT, high driven current, better for capacitive loads, ideal for mixed signal circuits. Disadvantages: more complex fabrication, higher cost, power hungry compared to CMOS. Applications: analog and digital mixed signal ICs, high speed buffers, RF circuits, analog front ends in the communication systems shown in the diagram. So comparison between your different technologies like NMOS, PMOS, CMOS and BiCMOS. The features are carrier types, speed, power, fabrication, cost and applications. Carrier type: in NMOS electrons, in PMOS holes, in CMOS both electrons and holes, in BiCMOS electrons plus holes plus or BZ. Speed: high speed in NMOS, low speed in PMOS, moderate, medium, high, very high. Power consumption: high statistic, PMOS also high, CMOS very low static, in BiCMOS medium. Fabrication: simple fabrication for NMOS, PMOS, moderate in CMOS, complex in BiCMOS. Cost: low cost for NMOS, for PMOS also, medium for CMOS, high cost in BiCMOS. Applications: NMOS are used in pull down circuits, PMOS are used in pull up circuits, CMOS are used in all the digital systems, BiCMOS are used in high speed analog and digital systems. Thank you.